The inverse scattering series, again, well, let's just say what it is. The word I was about to say is, I'm in awe of it. I'm in awe of it. It's sort of like Green's theorem, but even more so. You'll see things, no, when you're doing depth imaging without the velocity, and it has a density-only change, yes? It figures that out and doesn't bring that event in. Okay? We have Han Zhang and Hong, pioneers on that. That's amazing. All you had to do was make the inverse scattering series in a world which allowed for density change. And then you say, go find depth, only depth, yes? And it, in an integral, excludes reflections that only have density. If you said to me, figure out an algorithm that does it, I wouldn't know where to begin. We go in and we find out where it's doing things. Understood? That's very different than coming up with a... So these next slides explain the potential that resides within that procedure and what we're doing to mine it. So I apologize for those who've seen this many times. Scattering theory is a perturbation theory. Perturbation theory where you have a source which is assumed to be known in these methods. And if you don't know it, you have to find it. And Green's theorem helps us do that. Some source is assumed to be known. You have some medium, which let's say we consider a reference medium. And then a wave is generated by that source and enters and propagates within the medium and exits the medium. Let's say now you change something about that medium, anything. At one point you change the density or move a reflector. It doesn't matter what you do. Let's say this is the differential operator of the original medium. This is some impulse response. This is some idealized source. And then you change something about that medium and hence its differential operator to produce a new operator L corresponding to this perturbed medium. Any perturbation. And V is the difference of these differential operators, and hence whatever thing you did to change from reference to this new medium resides in V. This equation 1 is extremely important. It's an identity. You can prove it by just considering this like operators where that's a unit, and this will be L inverse, L0 inverse, L0 inverse, L0 minus L, and L inverse. And it's like sine squared plus cosine squared is 1. It's an identity, yes. It doesn't care acoustic, elastic, electromagnetic, Schrodinger, okay? It's an identity between the field, if you want, in the new medium, the original medium, and the difference in properties. And this field is here or here. So this is not an equation for the field. This is a relationship between the, if you like, the difference in field and the difference in properties. One way to make this into a modeling machine is to say the first estimate of this I'll call this. So then the first estimate will be G0 plus G0V, G0. Then take that as a new estimate and return that in that iterative fashion, and you get this series. This series, if it converges, is equivalent to that. Okay? It's just a geometric series. Okay? That's a very important point, that it's geometric. You get AR squared. This will come up later. The general way in seismic, and you'll hear when we talk about the difference between iterative linear, exactly the difference. And what this does for parameter estimation is our normal way to do model matching is Taylor series. The data at M equals the data at M0 plus a derivative, a Frechet derivative, a sensitivity matrix times M minus M0. That's a Taylor series. Okay? And we'll see what this says. This operator identity says that series that we just wrote down in terms of Frechet derivative you've lost some information. It's not Taylor, it's geometric. It's a very special kind of Taylor which has a structure that can be exploited. Because geometric series have inverse series, and Taylor in general do not. That's why they truncate it and they update it, because they can't find an inverse series for a Taylor series. Understood? Okay. So, but this is a very important expression all by itself. This says, this is a modeling machine, a perturbation modeling machine. It says if you give me the medium L, the normal way to find G is finite difference, finite element, reflectivity, lattice Boltzmann. You take the properties directly of the medium and you generate the weight. That's what those methods are. This says, don't give me the medium directly, give me it in terms of reference properties and this perturbation. And the reference properties enter this description in terms of the Green's function for the reference medium. And the perturbation enters as itself. But there's an extremely important message here. It says, if you have a medium L0 and you change it any way at all, the smallest amount, you move some reflector, you change some property one place or many places, any change in a medium will cause a change in the wave field which is nonlinear to that change. Nonlinear. Doesn't care what the change is. The most famous example of that is the Zopf's equations. If you have a homogeneous elastic medium, yes, and that's your reference, and then suddenly you change the half space to another medium, yes. In other words, the original wave is this. The scattered wave, the difference in G and G0 will be this, and then you transmit it, yes. That this reflection, the reflection off that boundary is nonlinear to every change, yes. Zopf's equation, and then you get Borfeld. You understand? That's a simple example of how a change from a reference produce a change in the wave field nonlinear to that. Okay. So that's a forward series. That's a modeling machine. The inverse problem is from measurements of G minus G0. In other words, measure in your phone what the actual measurement of the field is, and subtract what the reference medium would have produced in your phone. The difference between what your phone actually read and what a reference medium would have produced in your phone is called a scattered field, and measurements of the scattered field are your data. Yes? In other words, we don't have the scattered field everywhere, just where we measure it. In terms of measurements, the inverse problem is, can you find V? Because if you could find V, you assume you have chosen L0. If you can find V, you combine L0 with V and you find L, and you have the medium property. That's the idea. So V will assume that V is a series. And for those who haven't seen it, in other words, that forward series, G minus G0, it has a form G0, D, G0. Can you see this? Okay, and so on. So, if among friends, we can talk these are operators and intervals, and this has it can be derivatives in here, but just to keep it simple as a heuristic, imagine this is like a sum S. This is A, this is R, and the next term will be AR squared, yes, BG0, BG0. So you have this geometric series which starts AR plus AR squared and so on. Assuming that R is absolute less than 1, then you get a form here, AR over 1 minus R. The geometric, the first term over 1 minus the rate. You can solve this for R. If you solve it for R, you get S times 1 minus R is AR, and you get S is SR plus AR, and then R is S over S plus A. Is that right? Yes? So factor out the R, divide by S plus A. Yes? So you get this. So you can look at this as S over A over 1 plus S over A. And again, with all the conditions, you need to consider this a geometric, a sum of a geometric series. You can write this as S over A minus S over A squared, and so on. In other words, if S is a power series in R, then R is a power series in S. That geometric. So since the scattered wave, we call that S, is a geometric series with this R, then this R, which the main part of R that we're interested in is V, then V, it's reasonable that it could be a power series in terms of measurements of this. Yes? That's the idea. And with that thought, we then say, yes, this is that inverse geometric series, which is the inverse series, where this term is the portion of V linear in S. Or just like this is the portion of S linear, portion of S linear in R. This is the portion of R linear in S, quadratic in S. S is our data. Yes? This would be, well, would be R1. This would be R2, this guy. Meaning like V1, V2. So what we do is we take this form 3. So in other words, we say what we mean by V1. V1 is the portion of V that's linear in the data. V2 is the portion of V that's quadratic in the data. That's the meaning of it from this kind of inverse geometric series. And the inverse scattering series is just that, an inverse geometric series. Yes? So you take this form 3 and substitute it. Substitute 3 into the forward form. Take this form, and everywhere you see V, put that series, V1, V2, and evaluate this on the measurement surface, and set terms equal order in the data, equal on both sides. Set terms equal order in the data, equal on both sides. You can prove that that's rigorously true. Okay? We won't do that. If you want, I have to do it over lunch. So with that, on one side, you have the data. The only term on G0, V, G0 that's linear in the data is a term like this. All of the terms of V1 times V1, or start with V2, and hence are quadratic. This is the only term on the right-hand side of this. This will have V1 plus V2, this V1 plus V2. So the lowest order here is V1, V1. The only term in this whole series, when you substitute V in there, that's linear or first order in the data, is G0, V1, G0. And hence that's equal to the data, because the data is linear in itself. Yes. So you get this set of equations. You get that the linear in the data is the data. You get that the quadratic, what's the quadratic in the data on the left-hand side? 0. The data is equal to the data plus, there's nothing quadratic, yes? And so you get, that's where all these zeros come. So you add on the right-hand side, this is second order in the data, this is second order in the data. Terms of equal order in the data are set equal. That's the inverse scattering series. Yes. That's it. Are there any questions on that? Because this has profound implications. This has a whole different communication from Green's theorem. Yes? Green's theorem said, if you want to predict the field in the volume, you need to know the medium properties. Remember, there was an integral rho, and it had alpha in there. Yes? So, is Green's theorem not true? Of course it's true. They're both true. They're different. They're different data. In the Green's theorem, you're constricted to linear on the data. It's an integral, yes? On your P grad G, G grad P, it's a sum. This guy is talking nonlinear on the data, yes? It's a different use of the data. It has different, so let's see what, let's assume you're in the marine case, yes? And let's say we pick water as the reference. Then everything that's not water is part of V. So V will start at the water bottom, yes? Start at the water bottom, and whatever you need to perturb water to make Earth is V. So, but the reference medium is the Green's, the reference Green's function is what propagates in a homogeneous body of water. If you don't like that water is, we're assuming homogeneous, you can make part of the perturbation where it varies from homogeneous, or you can make the reference non-constant. The reference can be anything you want, and there are reasons that we pick the reference to be constant. Early on, in particular in imaging, we took the possibility of smooth background. In Fang Lu's thesis, we were hedging bets about should we make it homogeneous or should we give it some velocity help and then perturb. It wasn't clear, and we'll explain why we chose one versus the other. When you first start, how do you know? Why not use what you have, yes, and perturb from there? There was a reason we did. We'll get to that later. But the point is this: how do you get V1? You get V1 from your data and inverting this operator. These are water speed Green's functions. Then to solve a V1, if that's what you were interested in, you would do, in fact, a pre-stack FK slope migration with water speed, and out would pop V1. That's what it would be. In other words, you have these propagations, you depropagate them. Yes. You bring your source and receiver down, and you get V1 in an uncollapsed migration form, meaning keeping offset information. So the point is, to get V1, all you need to know is water properties and data. Once you have V1, you place it in here, where this is water. This V1 depends on water and your data. So this whole story here depends on data and water. And the operation you use to invert to get V2 is exactly the same as you use to get V1. G0, you just have to, there's an analytic inverse. Slope migration is analytic. Yes, you take data, you Fourier transform, you multiply these, yes, these phase shifts, and you integrate it. In other words, it's not a generalized inverse or something, yes? So the properties of this are every single term in the series is directly computed in terms of your data and reference properties. The reference medium never gets updated. There's one unchanged reference, and you keep getting more and more accurate estimates of that perturbation, yes? Understood. So that's a set of equations that has that communication. If you're looking for certain subseries, you don't even solve for V1. If your subseries that you're looking for is free surface or internal multiples, you're not looking for Earth. You just want a data map, data with and data without. Understood? When we do free surface or internal multiples, we don't solve for the Earth, yes? It's all a data in, data out machine. So the whole machine works keeping the sandwich, just looking at what's inside. Keep it in data. This is data, right? Every single step here is data. Only go to model space if you're forced to. Yes? So the point is that this is a direct inverse machine if you were after V. Direct meaning because you get a linear term analytically in terms of your data. And every single term after that requires a slope migration with water speed on that. And that only cares about water and your data. So you have a machine here which is direct in the sense that you can get V1, there's no search, there's no optimization, there's no generalized inverse, there's no math error surface, you understand? There's an analytic inverse, if you choose homogeneous background, for example, and you have what's complicated here. What's complicated here is these terms. But what they are data multiplies. If you say to me, would you rather take band-limited, noisy data and multiply it, or make an operator from it and invert? I don't have to think long. That's why the free surface multiple works well. It's data times data. There's no, if you do iterative, when you do iterative, it's a different story. Iterative linear has exactly the same point. The first term. You take that V1 though, and you produce a new L0. Let's say the original one minus V1. Update. And then you find yourself a new Green's function, G0 prime, and you do this. And you have G minus G0 prime. This operator, please look at this operator. This operator came from solving for V1. You had to find V1. V1 cares about your data. In other words, you have data, water, so V1 will care about data. What all the issues are in data will be in V1. And you're going to make a new L0 prime and a Green's function which will immediately be numeric. Yes? Numeric, and you're in the land of generalized inverse. Again, that's not evil, but you're in the land of math. You're not, you lose the physics. Okay? You lose the fact that the inverse is analytic, and hence all this machinery, you can see what their actions are. Okay? So, these two are not equal. So you might say, well, what is the difference? You're going to see that this afternoon. We'll take an example and actually run, yes, an iterative linear. Forget about it. We're going to give the method no noise, yes. Forget about the noise, yes. We're not going to give the iterative a noisy band limited. We'll give it perfect data. And we'll give it the inverse that this, we'll give it the linear inverse that this gives it, not Frechet derivative or sensitivity matrix. Give it a perfect linear inverse. But then let the iterative linear do its job versus inverse scattering. In other words, you understand? There go. Yes. And so that'll be interesting. We'll see that this afternoon. So anyway, the point is, all this wonderful math here, this whole, because we know other consortia are going to talk about the inverse scattering series now. This slide, taken as it is worthless, useless. Because, and we tried it. We means Paulo Carvalho, my first student in Brazil. Took data, primaries and multiples in 1D normal incidence and just calculated V1, V2, you understand? Just do it. And it worked when water, the actual velocity in the Earth was 11% different than water speed. Yes? But once you got beyond that, Ken Madsen independently got to the same conclusion. Test the whole data, put your whole data in, and the answer is it's absolutely useless. Okay? Because 11%, if it's bigger than 11%, that whole story diverges. So it's a nice slide. Okay? That's what it's worth. A nice slide. So, but it was, we were faced with this. So what we said is it possible to redefine our objective? Because we were younger and ambitious. We wanted to find the Earth, direct inverse, find the Earth. Yes, we could not find one, and there still is none for closed form. Not even for 2D Earth, there's no closed form, and we were very disappointed. We worked 2 years to find one, and we reluctantly went to the series as a direct method, but it was a series. We don't want a series. Why don't we want it? Because of this. Who knows what that's going to mean? The dots. So the first test was a complete failure. Yes? Meaning just put all your data in and go find V1, V2. Okay? The region of convergence makes it no redeeming social value. Okay? So why? Because that's an all or nothing idea. And we know most of the time all or nothing leads to nothing. Yes? So we readjusted our thinking. Yes? We said, this is the only direct machine we have. Is there something that's useful today that we could achieve short of everything that we might be able to locate here? Yes? At that time, multiples, radon was the method, and we were told by ARCO exploration people that multiples were a problem. The radon people within ARCO said that multiples were not a problem. They told me, that's not your business. Go do migration inversion. I went down to Brazil to work with Caballo on migration inversion. Came up, there was a visit during that year. There was all the business units from ARCO screaming, don't tell us you got the multiples out. We drilled and there's nothing there. That was like a shock to me. Went back to Brazil. Forget about migration inversion right now. Play about 3 and so on. We got to get the multiples out. So we had this story, and we said, look, if you have a machine which in principle takes data and outputs the Earth, it has some problem with convergence, nothing's perfect, but perhaps if you can locate these tasks, in other words, imagine that a machine like that, which promises in principle to go from your data and goes to the Earth, meaning V. Yes? Imagine that within that machine it has things to do. Get free surface multiples out, internal multiples, depth imaging, Q compensation, AVO, whatever, you know, all these things where we imagine as part of identifying the Earth. Perhaps you can identify where that activity is. Look, all of its actions all spread out here. Let's look at where these different activities reside, extract them, and see if they have better convergence properties, better treatment of noise, band limited, all of that we've got to care about. And that has been successful. Okay. There are terms in the series that do not, there are terms in the series that act as though the only problem in the world is free surface multiple. They are other terms that act like that term's interest is to do this and something else. You understand? Yes? We call it isolated term, isolated task subseries. Find the terms in the series that act as though there was only one problem in the world. Yes? That problem. That they had no other problem to do. So we go through and we locate free surface multiple removal terms. After we do that, there are other terms that are trying to do free surface and internal, and free surface and depth imaging, all kinds of combinations, yes? It just does, what does it do? It does whatever it can linearly, whatever it can quadratically, whatever it can cubically. That's what it does. It doesn't understand our interests, you understand? It's set up with its own machine. So what we do is we collect the terms that are doing free surface elimination, free surface multiple elimination. We make an algorithm. We input data that has free surface multiples. We output data without free surface multiples. We go back and we rewrite this whole thing as if there's no free surface. Yes? We rewrite it, there's no free surface now. Go start the problem again. Every time we achieve some isolated task, we restart, so we never deal with coupled terms. We think that the coupled terms are the reason for the divergence. Because all the series that we have for isolated, free surface, internal, depth imaging, Q compensation without Q, and and AVO, all of what we've observed, the isolated, have been convergent. So the problem's got to be somewhere, you understand? Okay, so that's been the strategy, and that's been successful. So the point is, if you pick a term or that's doing some particular task, every term, every piece of every term satisfies this property that it only cares about data in G0. You pull the term apart, it's still a part of a term. Only the ingredients, you understand? You're always getting that, that benefit. So I hope everyone understands. The issue here was try to find something practical in steps. By the way, we share that philosophy with Bruce Berkow in stages. Yes, do this, and after you do that, do this, and after you do that and that, then do this. The inverse scattering series says allows you to remove free surface and internal multiples, and then to do imaging. If it needed multiples to do imaging, it wouldn't let you get rid of them. There wouldn't be action in there to eliminate free surface and internal multiples if it needed it for other objectives. Understand? So, yesterday we showed that if you take Claerbout 3, yes? Not with this business, with Green's theorem, where you know the medium, yes? And it said, if you give me an accurate discontinuous medium, that multiples play no role. This machine here says, we're going to let you get the multiples out. It's arrogant that we thought it would. Why wouldn't it treat everything as signal? Didn't the multiples go through the earth? If this direct inverse needed multiples to do imaging, it wouldn't let you eliminate them. And we're all doing that today. I'm dragging things out of here that this does. Understood? In other words, there's an isolated task subseries that does the removal of multiples. And so that activity says that a direct machine, which works without subsurface information, agrees with what we said yesterday. If it needed it, it wouldn't let you remove them. Because there are things where we ask it to do, it won't cooperate. You understand? It knows what it wants. You follow? Okay. So this is a direct method, no subsurface information. It's a powerful combination, being direct. What do you mean being direct? You didn't see any search algorithm. There's no model matching here. It's just not trying to make the difference between a model data and an actual data minimized, yes, and updated, right? It's just, this is the linear term. This is the quadratic term, yes? It's not changing the linear term. The linear term is what it is from that equation. The next term is the quadratic term, yes? So, you'll see when we do that comparison this afternoon how different in terms of philosophy. Okay, but this is something that came to us in looking at this. This is something I'd like you to understand. There's two kinds of nonlinearity from our point of view. One is innate, and the other is circumstantial. And the inverse scattering series deals with both of them. So let me explain what innate is. If you have a homogeneous world, and that's the actual world, you don't have a problem to identify it. You know, if you send a wave, nothing comes back, you figure you got the right medium. Yes, I don't think we have to worry about that. Lose sleep over that. If you know something, yes, if there's some part of the world you don't know, you know and then you don't know, yes, then that causes a scattered wave which has a nonlinear relationship to that thing that you don't know, like Zopards. The only way I can see to avoid that nonlinearity is to know everything. If I know and then don't know, you're facing that business. Yes? That I call innate nonlinearity. The only avoidance of that is to know everything. There's another kind of nonlinearity which is like depth imaging. So if you have the velocity, depth imaging is not nonlinear. Yesterday, Green's theorem just predicts source receiver and you get the image. Understood? If you don't have the velocity, then the inverse scattering series says there's a nonlinear relationship with that reflection data that will give you the depth without needing to know that's circumstantial. In other words, I don't have to give you all the information in the world. There are people who were disparaging of Kleber. Nobody here is old to remember this, okay? They said, migration works well when you know the answer, when you know the velocity. So if I knew the velocity, what do I need you for? You know, if I know the velocity, what do I need you to place things, you know? They're missing the point. The migration doesn't need the velocity everywhere. It just needs the velocity enough to get to an image. You don't need to know the velocity below it. Yes? You're determining the unknown from some known. You're determining some unknown. You're not assuming you know that location. Yes? So I remember being in a company where they were joking about SEP. Because SEP was radical then. You understand? So the point is, the inverse scattering series treats these two very differently. For this, if there's a change there's an innate nonlinearity, it's there. Circumstantial, including multiples, it decides if you have a multiple or not. Anything that's circumstantial, for example, when we see the depth imaging without the velocity, it will decide on your data whether you have an imaging problem or not with the velocity you give it. It makes that decision. You don't. An integrand, you'll see, an integrand will be 0 if wherever you gave it the velocity, you happen to be giving it the right velocity, it won't do anything. In other words, as many of you heard me say, my fear when we went into depth imaging would be, we got a series. We have a series. So a series does series, you know? So let's say Scott gave us a C0 and it was right. But we got a series. So it's going to perturb. That was the word, you understand? Let's say C0 is right. Well, it doesn't. It makes a decision with your data whether the velocity you gave it is right. Yes. And if it does, it shuts down the first term that will act if it decides that your velocity was wrong. That's clever, okay? So circumstantial, for example, let's say you just, another example, let's say you just had a water bottom reflection. That's all, yes? And you put it into an internal multiple algorithm, yes? There is no internal multiple there, right? Just that. As soon as it gets to the second integral, it's 0. In other words, it says there's no, you don't have a, you understand? It makes a decision whether you have the issue it's set up for. So when you see the depth imaging, you'll see that. That amazes me. That amazes me, yes? That anything that's to do with circumstantial nonlinearity, it decides, is your linear procedure enough? Yes? And the term that would start to correct it, if it wasn't enough, it is analytically 0, and all the terms beyond it that are there to help send a signal, you're 0 too. I could never in a million years figure out an algorithm like that. It's in the series. You understand? I wouldn't know how to start, you know? How does it in the world do you? It's not common image flat, you know? It's not doing that kind of, you know, let me see if it's right. So, why is this here? Why is this capability here? It's one word. It's the word direct. It's the direct method is not looking, it's not searching. Every term in the series has a purpose. Well, in other words, there's a first term in the free surface multiple has a purpose. Because people say, how do you know if the internal multiple or the free surface is convergent? Well, we don't even need to know if it's convergent. The first term in the free surface algorithm does two things. every single multiple that's hit the free surface once is eliminated. And every higher order multiple is altered, getting ready for the second term in the series. And the second plus the first eliminate first order and second order. In other words, their purpose is identifiable. The reason they have their purpose identifiable is the method is direct. It's not searching. It's not, each term is doing something. Yes? And so, for example, Cavallo, he had a shallow water, yes, and a target such that he had 18 orders of free surface multiple that affect his target. Well, he knew how many terms to pick. If you have a different kind of deep water, right, different target, you know how many terms, because after a certain number of terms, you don't need them. It's not a matter of convergence. You know what they do. So that ability to know what terms do, we call that purposeful perturbation. We had no idea. We just thought it was plus, plus, plus. You understand? Dot, dot, dot. In other words, it could have been that we try to get all the multiples out a little bit, and then we try to get them out a little more, right? And then, you understand? And then we would know this is very different in terms of how this machine acts. So when I say I'm in awe of it, because the algorithms we have, including the internal, what came from looking at how the series acts, yes? We didn't dream up the algorithm, okay? We said, where in the series is it doing this, yes? Okay? Interesting. Interesting to me. Okay, this is what it says. Addresses a potential circumstantial nonlinearity, and only if it decides that it is. In other words, it will decide if you have an imaging problem or not. And if it decides you don't, it'll give you your conventional image. The first term is conventional. It's exactly what Claerbout 3 will give you with that velocity. Okay? Understood? That's interesting. That an integram would be that smart. We'll see that purposeful perturbation theory. Purposeful perturbation is because of direct. If we went on an error surface and start searching, you're lost in math. Yes? You lose the physics of what this is trying to tell you. Okay, so free surface multiples, I probably should have defined. A free surface multiple is any multiple that's hit the free surface once or more. Internal multiples never touch the free surface. They have prerequisites. They need the reference wave out. They need ghosts removed. So here's a very simple example. And I'm sure you're sick of having seen this before. But the lesson here is amazing. This example is going to show you how the free surface multiple acts and why it's not only independent of subsurface information, it's independent of Earth model type. Okay? It doesn't care if the Earth is acoustic, elastic, absorptive. It will play no role. You'll see it right here. Yes? So this is a cartoon of what the inverse scattering series does. It gives you some sense of it. So if you imagine some kind of unit pulse produces a train R of t, a frequency response R of omega, without a free surface, then this R of t has primaries and internal multiples, yes? Because there's no free surface. And R of omega is just its frequency response, straight up and down. This is the corresponding same experiment, except you have a free surface. Please notice, we in this derivation assume the wave went down, and what this is measuring is up. We have assumed it's deghosting. Yes? You understand? Deghosting is an essential part of what's going to happen. That's why up in that tree, is besides separating scattered wave from reference, is deghosting. If you'll see in this derivation how deghosting was essential. to get that algorithm. So there's a lot of value in this simple example. So the idea here is we're going to make this data from that data. We'll make the data in the presence of a free surface. In other words, this goes down, runs around here, and it has activity with the free surface, but there's no ghost here and there's no ghost there. It goes down, and what's measured here is up, but it doesn't mean it doesn't do that. Okay? It has free surface multiples, but the primaries, internal multiples, and free surface multiples are all deghosted. Yes? Because, you know, we write deghosted, but and you see results, and you'll see today results from Dr. Jinlong Yang with what happens to the free surface algorithm if you don't deghost. But let's see in the derivation where it was essential. Yes? So, we're going to create this, from this data, we're going to create this data. The idea is the following. If we had this measured in the ocean, if we could go from here to here, we remove the free surface multiples. Yes? If we go from RF to R, this has no free surface multiples. This has deghosted primaries and internal multiples. So how we're going to do that is we're going to derive this from that and then invert that equation. So so imagine what happens is this unit wave goes south through the water and then comes out from the Earth with primaries, a long train of primaries and internal multiples, yes? A train of events. Head north through the water column. Here, this guy. This and this train of primaries and internal multiples heads north. It heads north and it hits the free surface and picks up a -1. Every one of those hits with a -1 and heads south with a negative sign, yes, from what it arrived with. Okay? And that whole train of primaries and internal multiples is then like a giant wavelet that's entering the Earth, yes? A wavelet, a long train. So that you can imagine that one went down, R of omega came up, then minus R of omega went down. This is a train of primaries and internal multiples, yes? And it hit that -1 reflection coefficient, and that whole train turned around when south through the water column as a wavelet that enters the Earth. From the convolutional model, if a unit produces this, then this, as a wavelet, will produce minus R of omega times R of omega. This is the impulse response for 1, yes? So then sending this down will produce this up, and so on. This goes up, hits the free surface, picks up a minus sign, again goes down as a new wavelet. And that's what you see here. Up, hits the free surface, minus R, comes back, this goes, and it keeps doing that. Now what do? This guy, when it passes the foam in the water, is moving up. This guy, when it's passing the foam in the water, is moving down. Clear? Deghosting means we have this, not that, this, yes? We only collect the up wave. The down waves that are on the foam have been deghosted. So when you sum R minus R squared and so on, you get a series, and assuming R, which is a good assumption, is an actual value less than 1, you get what deghosted data that you would receive in the presence of a free surface is this geometric form. It comes from this, and so on. Okay? You just solve this equation for R of omega, and you get this. You write that series, This is the free surface multiple elimination series. Okay? What did we assume to derive it? We assumed a -1 reflection coefficient and a convolutional model. We didn't assume or know where the water bottom was, right? We don't know how many layers you have, whether it's velocity, density, acoustic, elastic, absorptive. As long as the convolutional model and -1 is in place and deghosted, yes, then you have this algorithm. That's what we mean by model type independent algorithm. Yes? Okay. So the internal multiple has the same property. And you'll see Jing will show you examples today with absorptive, dispersive medium, how that works. With a reference which has an acoustic, yes? And then you'll see Yang Li with acoustic reference, elastic medium. PS waves, yes, elimination, where the medium is water. The reference medium is water. Shear wave doesn't even exist in that reference medium. And yet the algorithm, model type independent, doesn't care what the actual Earth is. So this is, so that's one lesson here. The other lesson is, as Bill Drager said, probably taught us, this is the data, your original data deghosted with the free surface. When you add this to this, two things happen. And you can show that analytically, is every multiple that's hit the free surface once is eliminated. And every higher order free surface multiple is altered so that when this plus this happens, every free surface multiple that's hit once or twice is eliminated. The free surface, every single task in the inverse scattering series has cooperation. No term there does something complete on its own. Yes? Free surface, not internal. It all has something it can do, something it can't do. Then with that, something more gets done. What this will do, this will not take out second order unless this one prepped it. Prepped the second order. Interesting, that cooperation. Yes? So that's also part of this purposefulness, yes? It's not just, let me do a little more. We know exactly what these different terms are doing, so we know how many terms to take. And there are examples here of invisible. So this is very different. This has a strength and limitation. If you have a clear multiple, there are times, as I said yesterday, this free surface and internal multiple business is not always the method of choice. There's an amplitude being predicted here. You're predicting a trajectory, yes, the amplitude and time of an event. If you don't need that, let's say you have a radon doesn't predict the amplitude, just predicts cuts on a trajectory, yes, and do it. This is prima donna method. Doesn't want ghosts, it wants a wavelet, right? It wants data. So what I'm trying to say is, in the old days when you had deconvolution and you had random primaries and periodic multiples, people would say when we looked at this, what are you going to do if you have an interfering primary multiple? Because that's not understood there, yes? Here, it's an amplitude issue. So here's an example. This is just showing you the action. Here's an invisible, we're going to show you where a primary and multiple completely cancel. This would hooked up this is a primary, this is a free surface multiple, this is another primary, yes? Arrange for these two to cancel, so they're not in your data, yes? You understand? The data is only going to see that first primary. So we arrange the time of the multiple to be the same as the time of the deeper primary, and we arrange the amplitude to be equal and opposite. That's all. Yes? It's not hard. And Bill has examples. Where's Bill? There. Examples with offset like that. Yes? It's the fact that it produces, so, in your data, all you're gonna get is this one thing that's recorded, right? There's a second primary and there's a free surface multiple that you get, they're right here, 0, that's 0, because they cancel. Yes? So how is it going to recover the second primary? Yes? It takes this, puts it in the frequency domain, in other words, look at the algorithm. The algorithm says, take your data in this simple case 1D normal in the frequency domain, multiply it by itself and add it to itself. Yes? That's what it says. In that case, your data is only one event. Right? Because these two cancel. So you got one event. You put it in the frequency domain, square it, add it to itself. And guess what? Now you have two primaries. You understand? It recovered the primary that you couldn't see. Listen, yes? How? That's not magic. You told it something that it used. You didn't just give it a primary. You gave it an algorithm which was for free surface multiples. Yes? So you told it there's a free surface. In other words, that R of omega plus R omega squared, that's a machine for removing free surface multiples. Yes? So it says, look, I'm not going to argue with you. You said that's the algorithm must be a free surface. In other words, the inverse scattering series will argue with you with information you give it below the measurement surface. Above, as soon as you got your head screwed on straight. Yeah? You understand? It assumes that you know what you're talking about above. Below, if it doesn't agree with the information, it will make an adjustment. It'll say you didn't have the right velocity. You understand? Above, so once it knows it's a free surface algorithm, right? It assumes that this primary can't be the only thing there. There must be a free surface multiple, because you said there's a free surface there, right? That's what the algorithm assumes. Understood? So it anticipates if you're there, there must be this that's there that I have to subtract. So when it subtracts that, out comes the second primary. That's simple. But you can see how it doesn't depend on you seeing things, right? But there's an amplitude issue. And so there you go, get the two. So this is the grown-up version of it. As a sponsor, this is what's important. So Carvalho, this factor here is what Delft does not have. The SRME does not have this. So if you look at when I came back to ARCO from Brazil, and we had Carvalho's results, what they were shocked about was the fact that it worked pre-stack and post-stack. The SRME would look good pre-stack, but when you stacked it, the multiple came back because it didn't work equally well at all offset. Because of this missing, this is square root of omega squared over c squared minus k squared. So there'd be a residual large offset multiple, yes? And when you stacked it, the multiple looked like it came back. This is equally effective at all offset. When this is more expensive than SRME, but if you have a multiple that's interfering with a primary, this kind of multiple, I'd pay the price. Again, it depends. Would we use SRME at ARCO if we had a free surface multiple that was sitting by itself? Of course we would, rather than this. And if we needed to touch up with adaptive, we would do that, yes? But not if you have some interference, yes? Then you want a clean removal. Okay, and then we have the internal algorithm, that's Araujo and company, and more complicated. This B1 is a water speed stall uncollapsed migration, Claerbout 3. So basically what it's saying is, we don't have the Earth. If we water speed image events, maybe they would, if A real multiple is a real internal multiple is doing this in a real Earth. We don't have a luxury of knowing the real Earth, but we assume we don't have any information. A real multiple does this. So there's some lower, higher, lower in real depth. Yes? What this is assuming is that if you take these events and you image them with water speed, yes, you're not going to get the right depth, but they'll have the same relative relationship to each other as the actual multiple. Yes? And this is not looking for depth, this is looking for time, data in, data out. Yes? So that's basically the story. This is a recent example of a thesis work done at Petrobras. You've probably seen it. Very impressive work. Where's Paolo? Paolo Dringi worked with Andrea Correa. Okay. And Paolo is with us. And there's a salt layering on the right there. The first pre-surface multiple. Then internal. With a focus on a piece. We should say these algorithms are extremely expensive. Michael Perrone wants to communicate from IBM that they, some years ago, did a comparison on different architectures of these algorithms and reported a formal report to the sponsors. That's going to happen again with the new capabilities since 8-10 years ago when they did that. What is the new kinds of compute capability? How will that affect our 2D and 3D internal multiple algorithm? So Michael, today is his birthday, the 5th, so he's not here. Perrone at 5 p.m. But he sends his regards, and there's a plan for them to test. Yes, and probably have interns going there up in Yorktown Heights. Yeah. So there's a piece here that and that's the after. Before and after. How to make no small apartment, that's expensive. And the Petrobras result, no other method that they have, had similar effectiveness. On and on, that same story. So I think the next talk, we'd like to thank the sponsors, is Chung, yes?